Hello and welcome to this video about vector space proofs and trying to bring them to life with pictures and explanations. So this is an example of a subspace. Let V be the space R3. Then an example of a subspace of V would be a flat plane that crosses the origin, which we can call W. And here are some vectors that we'll be using: x, y, z, the zero vector and the negative of x. So we'll start with this theorem, that W is a subspace of V if W is a vector space and a subset of V. We'll be able to reduce this to 4 points. So W must contain something. If it doesn't contain anything, then it can't be a vector space. And W must be a subset of V, so that everything in W is contained in V. And this statement must be true, and it's the first axiom of vector spaces. You can see here that W must contain at least one vector that it can add to itself. If it contains more than one vector, then it has an infinite amount of vectors, which makes it more interesting. And this statement is the second axiom, and W needs at least one element to satisfy this too. So now to look at the first point, that W can't be the empty set, represented by phi here. It can be represented by empty brackets too. It turns out that it must at least contain the zero vector, which we'll prove later, so it must be non-empty for this condition too. And it needs something in it to do points 3 and 4 and a lot of the axioms that we'll be proving. So the next point is that W must be a subset of V, so that everything that's contained in W is contained in V. And this can be expressed as this logical statement, which we'll make use of. So these are the next two statements that will need to be true. And they both satisfy the first two axioms necessary to prove that this set is a vector space. So now to look at the concept of inheritance. W inherits all of its members from V, which is sort of its parent vector space. And therefore it will inherit all of its properties. So that we can use this to prove all of these axioms, but we'll only have a closer look at 3 of them. So we'll use inheritance to prove axiom 3. Any two elements that are in W will satisfy this addition symmetric property because they are in V, and V is a vector space. So this holds for all the elements in W, and so we've proven axiom 3 for W. And we can use inheritance to prove axiom 4 for W. We need 3 vectors this time. And this associative property holds for these elements because they are in V. And so axiom 4 is satisfied for all of the elements in W, so we've just proven axiom 4 for W. So now to have a closer look at axiom 10. So we'll just state inheritance here again. And so we know that 1 is a scalar for the vector space V, and also for W, even if it isn't a vector space. So multiplying any vector x by 1 will give the vector by itself, because x is a member of V. So this satisfies axiom 10 for W. So we've proven all of the axioms that can be proven using inheritance. So now we're left with only 2 more axioms to prove, that is 5 and 6. In axiom 5 we have to show that W contains the zero vector, which is obvious, but must still be proven. Well, 0 is a scalar for both V and W. So any element of W multiplied by any scalar will be an element of W by axiom 2. And we'll use this theorem that we've proved earlier in another video, that multiplying any vector by 0 gives us the zero vector. We can use this theorem because x is an element of V, which is already a vector space, unlike W, which still needs to be proven to be a vector space. And therefore the zero vector must be contained in W, because it is equal to 0 times any other vector in W. And so we've proven axiom 5, the existence of the zero vector in the set. And now to prove axiom 6, which is the last axiom that we need to prove. In order to prove that W is a vector space, we need to show that W contains all of the negatives of all of its elements. We'll do this by using the element x, which can stand for any element and therefore every element in W. So this time we'll use the number -1. We'll state that -1 is a scalar for both W and V. So using axiom 2, we can multiply any element of W by -1 and it will still be in W. Then we can use a pass theorem to show that this element will be the negative of x. We can use this theorem because X is an element of V, which is already a vector space, and all elements of W are contained in V. And therefore the negative of X must be contained in W, because it is equal to an element of X multiplied by a scalar. And so this proves axiom 6 to be true. Finally, we have proven all 10 of the axioms to be true for W. And this proves that W is a vector space. And because W is both a vector space and a subset of V, then W is a subspace of V. And we can write it like this using a less than sign. V and W aren't numbers, and so this sign can't operate like a less than sign. So it must operate as a subspace sign. So I hope that you've found this video to be insightful and helpful for your studies in linear algebra. Please click like and subscribe if you did. Please leave some helpful thoughts in the comments. Feel free to share this video, and thanks a lot for watching.